Good morning, all of you TyBscPhysics student. We have to see here our subject is solid state physics. And we want to continue fourth chapter, which is the magnetism. In this chapter, last 2 to 3 lecture, we have to discuss here idea, the study of the magnetism, what is meant by the magnetization vector, what is meant by susceptibility, and what is the condition of the diamagnetism, paramagnetism and ferromagnetism, that substance which is placed in the external magnetic field. If substance placed in the external magnetic field, so that diamagnetic substance which are weakly repel. For paramagnetism, that substance which are weakly attracted, and in ferromagnetism, that substance which are strongly attracted to each other. And after that, we have to see here the point of the conductivity or superconductivity. That superconducting substance which has denoted as the substance which has zero electrical resistivity at low temperature. So that substance which mean by the superconducting substance, and what is the property of type first superconducting material and type second superconducting material. Okay, in this chapter we want to see the next point, which is considered as the paramagnetism. In paramagnetic substance, that each atom contains the permanent magnetic dipole moment due to the thermal agitation, and these dipole moments are randomly oriented in the material at giving the zero net magnetic moment in the absence of the external field. So these moments are due to the intrinsic electronic spin and the orbital motion of the electron. So first of all, we have to consider here in diamagnetic material, so that material contains upon with the effect of the electronic spin in the shell or orbiting of the atom or the material. And in both paramagnetism and ferromagnetism, that substance which related to intrinsic electronic spin and orbital motion of the electron. So this substance which is placed in the external magnetic field, so this shows the weakly attraction of the electrons in the material. So if we place the external magnetic field B bar, which is applied the magnetic dipole moment of the atom which are oriented along the field direction, and as compared to diamagnetism, we have to see there that magnetic susceptibility which is negative and field direction which is opposite to each other for magnetic field direction and magnetic strength, and magnetization vector and magnetic field direction which is oriented opposite direction. While in paramagnetism, that the moment of atoms are oriented along the field direction, and because this phenomena which is obtained, the energy is lower when the magnetic dipole moment is parallel to field, and then when it is anti-parallel, so that parallel alignment which is prepared due to the induced field in the material which adds to the applied field, so that susceptibility is positive. So this is the main point, because we have to know that in diamagnetic material that susceptibility is negative, and in paramagnetic material that susceptibility which is positive, and tendency of this magnetic dipole moment which is aligned along the applied field direction and is opposed by the thermal motion which tends to the make the direction of the magnetic dipole moment which is random. And we have to see this paramagnetic susceptibility which is given as the negative, so that this conclusion for the given formula, which is the simplest kind of the system of the paramagnetic susceptibility, and that containing the separated atom, and that magnetic moment of atom in the free space, that is denoted by mu bar, and that magnetic moment which is considered as minus g into mu b into j bar, and this mu b is called the Bohr magneton. So that mu bar is equal to minus g mu b j bar, so mu b is called as the Bohr magneton, and small g which is considered as the Landé G factor, and this Landé G factor which is calculated by below this formula. So that G is equal to 1 plus J into J plus 1 plus L into L plus 1 plus S into S plus 1 divided by twice J into J plus 1. So this formula which is given by the Landé G factor, and here J is denoted as the total angular momentum. We have to take here value and we have to calculate the Landé G factor formula, and which is placed in the above formula. And this mu b is called as the Bohr magneton, that SI unit which is called as EH cross by twice m, and it is numerical value. It is numerical value which is considered as 9.274 into 10 to the power minus 24 ampere meter square, and which is considered in 9.274 into 10 to the power minus 24 joule per Tesla. So this is the magnitude of the magnetic dipole moment which is associated with the value of the total angular momentum, and this is which is given as mu into g mu b into under root of j into j plus 1. Also we have to g which is calculated by this Landé G factor formula, and we have to know that corresponding that j of j plus 1, that is total angular momentum with respect to that orbital, and which is calculated by the angular momentum as well as the spin angular momentum. So that factor we have to calculate here simply the j, and we have to calculate this mu bar. So if that external magnetic field B which is applied to the material, so that the energy level of the system of the magnetic field which is given as that potential, so that U is equal to minus mu dot B bar, and B bar here the magnetic induction or magnetic field intensity, and this is calculated by small mj into g into mu b into b, and this small mj which is value calculated by the spin azimuthal quantum number or spin angular quantum number, and this mj which is called as the azimuthal quantum number, and the values of j which is considered as calculated by this, that j minus 1, j minus 2, 0 to j plus 1. So that value running from j minus 1 to j plus 1, and for the single spin with no orbital motion, that mj is equal to considered as the plus or minus half, and g is equal to 2. So hence we have that potential, that magnetic field are considered as U is equal to plus or minus mu b into b, and this splitting into two split line, so that which this phenomenon which is considered as without applying the field, and that consider the field value which is considered as that spin angular momentum, that is plus or minus half and plus or minus half. So that upper side spin which is considered as up state which is plus half, and down state which is considered as minus half, and that orientation which is considered as minus mu and plus mu. So see in the last lecture in the diamagnetism, there also we have to consider classical diamagnetism theory, or which is also called as the Langevin theory of diamagnetism, and also in this concept we have to see here the Langevin theory of the paramagnetism. Okay, and in this theory we have considered that system considered as the separated atom, and in each of the atom that electron orbital angular momentum is 0. Electron orbital angular momentum is 0, and there is unpaired electron with two space orientation of the spin. So let us consider as here that N is the unpaired magnetic dipole moment. N is the unpaired dipole magnetic moment of electrons per unit volume. And here that N is equal to consider as N minus and N plus, that N plus represent the same moment for anti-parallel to the field, and then this formula which is given as N is equal to minus N2 plus N, and the magnetic potential energy for this electron which is parallel orientation with the field direction which is minus mu b. So this orientation or this field orientation which is calculated within this splitting lines which is 2, which is described the above figure 4.9, and due to that, so that we have to consider as the microscopic system. So calculated this, how it is obtained the minus mu b. This is the calculation part will be further in the next lecture we have to see here. And this field direction which is minus mu b, and with consider this the anti-parallel orientation which is considered as the plus mu b, and this is calculated by the Boltzmann distribution law, that the number of electrons in energy state, this is the parallel to the field. So if we doing the calculation for this, consider as the N minus, that N minus which is considered here, so that the spin alignment which is moment is parallel or anti-parallel, so that N minus value which is considered as here A into N into e to the power minus mu b by kt. So here A which is considered as the Boltzmann constant value, and N plus which is given as A into N into e to the power mu b by kt, and this resultant of this magnetization, that is the magnetic dipole moment per unit volume, which is given by the formula M is equal to mu into N minus minus N plus, and we have already calculated this value according to the Boltzmann constant. So that alignment of the spin which is parallel and anti-parallel. So putting this value in this equation, so that we have to see here that Boltzmann's constant which is common in this formula, so we have to take in outside of the bracket, and putting this value that e to the power minus mu b by kt minus e to the power minus mu b by kt, and this if we calculate the average net magnetic moment which is given by the formula, that mu bar is equal to M by N, and this M which is calculated here the above formula mu a n e to the power minus mu b by kt minus e to the power mu b by kt, and denominator n minus n plus, this is above calculation which is here a n into e to the power minus mu b by kt, and where plus which is a n e to the power minus mu b by kt. So putting this equation or this formula in this equation, so we have to get that average net magnetic moment which is given by mu bar is equal to mu into e to the power minus mu b by kt minus e to the power mu b by kt, and denominator the plus sign which is between this which takes place is there. So that is the formula of the average net magnetic moment which is given by here, and this net magnetic dipole moment per unit volume, that is magnetization, which is calculated by simply say that M is equal to N into mu bar, and putting this value in this equation, so we have to get here equation that M is equal to N into mu e to the power minus mu b by kt minus e to the power mu b by kt divided by e to the power mu b by kt plus e to the power mu b by kt. So putting this equation, we have to get the idea upon idea which is given as the magnetization vector in the paramagnetic substance. So this is the calculation part. We will be see in the blackboard lecture after completing this this chapter. Very well clear get that time we have to get clear idea, but simply understanding the here. So how we have to calculate here the magnetic dipole moment or magnetization vector, so using this formula. So if we since the consider as the circumstances that mu b factor which is much less than kT, that is which is that temperature is higher in this. If we increase the temperature, so that gives the expression that e to the power mu b by kT, which is given as 1 plus mu b by kT plus, and e to the power minus mu b by kT, which is given as 1 minus mu b by kT plus, and so on. So using this equation we have to get formula that consider as m is equal to that given relation is here, and if we calculated this term by cancelling of each other, so that formula which is given as n into mu square b divided by kT, and here b that magnetic field intensity or induction, which is given as mu naught h, that is permeability into magnetic field strength. And this equation we have to get idea here that m is equal to n into mu square into mu naught h upon kT, and the magnetic susceptibility which is given as chi is equal to m upon h, and this x, that magnetic susceptibility, we are putting the value of this above equation 4.24, so that value which is given as n mu square mu naught divided by kT, and this hh, that magnetic field strength, which is get cancelled, and this is the Langevin result of the paramagnetic susceptibility. And this equation which is given by the final resultant equation chi is equal to c by t, and here the equation which is called as the Curie equation, that chi is equal to c by t, and that constant which is given as n mu square mu naught by t, and this is called the Curie constant, and the equation which is considered as 4.26, that is chi is equal to c by t, that shows the susceptibility varies inversely as the temperature, because we have to know that c is equal to n mu square mu naught by t, so that relation which gives the idea that c is inversely proportional to t, and we have to that relation we have to get analyze this graph, so that consider as the plot of the magnetization m, and that applied field b, so that applied field which is show as the horizontal axis, and magnetization m is the horizontal vertical axis, so that gives the value of the nature of this formula, so that is given as this temperature, so that is the graph which is exponential nature which haven here, so that shows that the Curie constant or that susceptibility which is varies, which is inversely to this t. So this is the idea about the paramagnetic substance. So in this chapter we have to see here, so that clear that idea, so that paramagnetic substance which is considered as if we this substance which is placed in the external magnetic field, so it is weakly attracted to each other, and here the susceptibility value which is given as the positive, and that alignment which have this substance shows the dipole magnetic moment, but when if not external magnetic field applies, so that does not show the permanent dipole magnetic moment. And this formula for according to Langevin theory, so we have to calculation this. So what is the value of the magnetization vector, what is the value of the magnetic susceptibility, and that graph shows the variation of this susceptibility, so that given the idea how is it the type of the behavior of the paramagnetic substance which is shown in here. If we have any queries in this lecture, so we have to see also on the next lecture, special lecture on this theory, which is very interesting, which is see in the next after 2 to 3 lecture. So thanking of you, all of you students.